All right. Last lecture, we learned about rocks. And honestly, I know that wasn't a very exciting topic. We talked about the different types of rocks and the ones that are silicates, which is, 90% of the rocks, and the ones that aren't silicates, things that are not based on silicon dioxide. And we talked about how they're made, how you have the igneous rocks that were molten magma that freezes. We have the sedimentary rocks that were rock that has been eroded and then compacted together. And then we have metamorphic, which could have been either and has been heated and transformed through pressure, heat, and actually water as well. And then we talked a little bit about the structure of the earth. Well, today we're going to get a lot more into the structure of the earth, how we know about that structure of the earth and what the earth does. So at least in my opinion, this is going to be a lot more interesting topic. This is not chapter 21, by the way. Okay, so let's get into it. Seismic waves. Seismic waves, we usually just talk about earthquakes. Seismic waves are the waves that make the earthquake. And so when rock under the Earth's surface slips, now it says here moves or breaks, what we have is what we call faults. Faults are places where we have essentially two rocks, and when I say rocks, I mean big pieces of the earth that are not really held together. They're just against each other. And of course, there's pressure pushing against them. So they stay there, but you can build up stresses. You can have things that pull this one this way and pull this one this way. And over time, those stresses get bigger until it slides. And when it slides, well, that's a huge energy release, and it sends waves traveling through the earth, and we call those waves seismic waves. So geologists study those waves traveling through the earth, and they use those waves to infer what's going on inside of the earth. So here's another cutaway view. We saw something like this last lecture where we have the crust out here, the upper layers, the crust, and then we have the mantle. Remember, the mantle actually has the upper and lower mantle. And then we have the outer core and the inner core, the four pieces of the earth. And we know about those because of studying the seismic waves. And it's important to know that we have two types of bulk waves. Bulk, I'm going to rewrite that because it looks like an A instead of a U. They're waves that travel through the bulk of the earth. And a primary wave is a longitudinal wave. That means that the motion of the waves, the particles like the earth moving, is in the same direction as the direction the wave is traveling. The secondary wave is a transverse wave. Transverse meaning that, come on, move back. For some reason, it won't. There we go. Transverse meaning that the motion of the earth is perpendicular to the direction that the wave is traveling. Those are only two types of waves that travel through the bulk of the earth. The primary wave is also called a pressure wave. The secondary wave is also called a shear wave. Primary means it's the first. Primary wave is faster. The pressure wave is faster, hence primary. The secondary wave or shear is slower, hence it comes second. So those are waves that go through the bulk of the earth. Then we have surface waves. If you're on the surface of the earth and an earthquake comes, you have different types of motions. The love wave, the motion of the earth here is moving left to right, and the velocity in all of these is traveling to the right. Okay, in and out as the picture goes for the motion, and it's traveling to the right. So the love wave, you go side to side as the wave passes. The Rayleigh wave is kind of like an ocean wave. An ocean wave, when the wave comes to you, so if you're here in the water and the wave is coming at you like this, your motion initially you're pulled into it. Then it lifts you up, and then it pulls you to the right, you come back down. And so you actually do a circle when an ocean wave travels. The Rayleigh waves are kind of the same thing, except for you're going the opposite direction. So in the Rayleigh waves, the particles are moving like that. So that's a rolling type of motion. Up, forward, backward, down, forward, up, backward, down, forward, up, backward, down. So those are surface waves. They only occur on the surface of the Earth. And I have here a link to a video you can watch on your own to see the illustration of those different types of waves. Now, how geologists study the interior of the Earth is by knowing what happens when waves change speed. If you have a change in speed, the wave will actually bend. And if you have a distinct, abrupt change in speed, then you'll have a distinct change in the direction it travels. And they can determine the densities of the different layers based on the velocities that they see. So how do you get the velocity? Well, number one, you measure the time it takes to go from point A to point B through the Earth. And then there's more calculation than that, but that's the primary thing for us to think about. Now, a little bit of history of our understanding of the Earth. In 1906, so that was 114 years ago, Richard Oldham observed that the P waves, the primary waves as we call them, or pressure waves, and the S waves, the secondary or shear waves, they travel together for a distance, but then they encounter a boundary where S waves stop and the P waves refract. So stop, that means the S waves they disappeared. Refract means bend. So the P waves bend, but the S waves stop. And what he had discovered was a barrier where you had liquid and solid. And S waves can only travel through solid. They cannot travel through a liquid because liquids can't support a shear. But pressure waves can travel through both a solid and a liquid. And so if you have waves traveling together that come here, so we have the P wave can go through, the S wave stops. And of course it does refract, it's going to bend. My picture doesn't show any bending. And so what he discovered was that there was a liquid layer in the Earth. And by careful analysis, and I have a picture of this coming up in the next slide. By careful analysis, he was able to determine what the radius is of that liquid layer. Then just 3 years later, Andrija Morovičić, I can say his last name, observed a sharp increase in size of velocity in a shallow layer at the Earth. And so this is just a change in velocity, right? Change in velocity. It's not one wave stopping. So it's not a liquid barrier, but it's a distinct change in the density of the material. And we now understand, we call this the Morovičić discontinuity, because you have a discontinuous change in the density of the material. And so that's where we put the boundary between the crust and the mantle, where you have that distinct change in the material. So here's a picture. And the first thing you can see is when you look at the work of, was it Oldham? That it's interesting because I have another screen where I'm looking at, Oldham, just didn't see his name. What he discovered was you have both S and P waves here, and then you have a distinct refraction bending there. So there's a region where there's no waves, and then you have only P waves here. So there's no S waves that continue once it hits that liquid, and the P waves bend a lot, leaving you this shadow zone, place where you don't get P waves. Now, I think I mentioned this before, but just to be clear, the epicenter is the point on the surface of the Earth above where an earthquake occurs. Another name for where the earthquake occurs, so that's not where the earthquake occurs, it's on the surface. Where the earthquake occurs can be called either the focus or the hypocenter. So when people talk about epicenter, they're talking about a location on the surface of the Earth. Just, things to know. So we were moving forward in time. We had 1906 that Oldham had discovered that you had the P wave stopping and the distinct change in speed. And then 1909 when Mohorovičić found his discontinuity. And then in 1913, another 4 years, Bino Gutenberg refined Oldham's work, and he determined that this radius right here was 2,900 kilometers, the radius from the center of the Earth to that edge of the liquid boundary. Now we move forward a fair amount of time, 1913 to 1926. That's 13 years. Harold Jeffreys determined that the core, part of it must be liquid. Of course, I just described because you don't have the S waves going through, it's liquid. And part of it, on the other hand, must be solid. Now, that's not something we had talked about. So what he determined is you have the core and you have solid in the middle and liquid outside. How did he determine that? Well, it actually is kind of complicated. You have the P waves that come in and go like this. And when the P wave hits here, it makes a surface wave that goes like this. And then that surface wave sends out its own wave. So we're looking at waves that are produced by the surface wave going over that solid boundary in there. So that's actually how Jeffreys determined that there was another solid layer inside. And so if we put this all together, we get the, actually, wait, I thought that it was Jeffreys, but apparently Layman's the one that determined that there was the solid inner core. Boy, got that one wrong. Still by the same method, though. So we put it all together, and these are the pieces we have. The core is composed of primarily metallic iron. How do we know that? It's, let's say, a guess. Iron is the most dense, quote, common, end quote, material on Earth. Now, there's lots of uncommon things that are more dense, but it's the most dense common thing. And so based on more dense things sinking, we believe that it's primarily iron with nickel, and so metallic, that core. The solid core is solid because it has such great pressure that it forces it to be solid, even though it's really hard or really hot. Outside of that, you have the liquid stuff, just it's less pressure so it can maintain liquid. And that liquid core, we believe, makes the Earth's magnetic field. We know that if I have charge going around in a circle, it creates a magnetic field. And so our understanding is the Earth has metallic conducting material that's going around in circles, and that's what creates our magnetic field. We believe the sun does the same thing. Now, the sun's magnetic field is not made by iron. It's made by liquid metallic hydrogen, but it's still metallic, and that metallic hydrogen swirling makes its magnetic field. So here is, instead of looking at it as a sphere, we're just looking at it as a block. So you have the inner core that's solid, the outer core that's liquid, then you have the mantle, and then you have the Mohorovičić discontinuity. It's just called the MOHO here, where you have the boundary between the mantle and the crust. And finally, notice that the crust has the thicker region here that's continental, the thinner region here that is oceanic. Once you get down here to the mantle, it's extremely uniform from everything that we can determine. Very uniform down there. And the crust is floating on this stuff underneath. I know it sounds wrong to talk about floating on. We think of the Earth as very solid. But the fact is that we are floating. And so the weight above here is going to be the same as the weight above here. But there's a much thicker region here because it's less dense. So you have to have more thickness to have the same weight. This, I know it may sound really bizarre and not right, but here's something that's actually been observed. When you have a glacier, you have a big load of ice. And that big load of ice, of course, has a pretty big weight. And so what happens is that the crust sinks down a little because of the weight of that ice. But when the glacier melts, then it will spring back up. Now, not spring back up in the course of days or even weeks, but over years, it will rise up. The surface will slowly rise up because it was depressed because the weight on top of it, and it's floating. So it's just like when you have a canoe, you get in the canoe, it sinks down, you get out, it comes up. That's what the surface of the earth does. It just happens a lot slower because of it's much less pliable. The mantle here, notice, is divided into two regions, the upper mantle and the lower mantle. And the difference in the mantle is, notice it says asthenos or plastic. Plastic means it can be deformed. And so it's kind of solid, but it can be squished around. And so the asthenosphere is the deformable region on which the lithosphere, the top region, flows. And so we'll talk about that coming up. We're going to end with plate tectonics and evidence for it. So the lower part of the upper mantle is the asthenosphere. And when I was studying this, they said, think about it like the grease on which the tectonic plates slide. The lithosphere, litho means rock, and so that's the uppermost part of the upper mantle and the crust. The lithosphere is the stuff that slides around on the top of the asthenosphere. And so it's rather cool. By rather cool, we mean it's cold enough that it's a solid rock. It doesn't float, but slides on top of stuff. And it can be broken up into individual plates. So this picture here, picture says 1,000 words, they say. If you have a mountain up here, you also have to have a root down below. Just like with icebergs, about 10% of an iceberg is above water. And you've probably heard that. That's why they say it's just the tip of the iceberg, because most of the iceberg is below water. So what you see is just a tiny part of it. Well, it's the same thing with the mountains. If you have a mountain that's sticking way up, it has to be also pushing way down, because remember, for things to float, they have to displace a fluid with mass equal or weight equal to the weight of the floating object. And so this continental crust has to displace Earth that weighs the same amount as the crust. Now, the crust is less dense, so it floats, but the heavier you make it, the more the root's going to sink. Now, the ocean crust is much more dense than the continental crust. And so because it's more dense, it's not nearly as thick. It would sink way down if it was thicker. But because it is more dense, it sinks down, and that's why water fills in those basins. So now, I know in yesterday, or in our last lecture, the graphic said something like 5 kilometers thick for the oceanic crust. This one here says 10 kilometers. 5 is really a very minimal number, like the thinnest it ever gets. And 10 is the average thickness. And the continental crust, notes 20 to 60 kilometers. 20 kilometers if you're here close to the seashore, and 60 kilometers if you're under a mountain. And granite, as dense as we might think rock is, it's low density compared to the rest. Isostasy is a word meaning equal standing. And we say that we have the floating of these layers up here because of isostasy. They reach their balance. You know how they say water seeks its own level. The crust seeks its own level. They reach their balance because they're all in equilibrium. They're all floating on this same upper mantle. So that's what the isostasy is referring to. Yeah, I'm going to skip right by that. It's nothing new. I've already talked about it. Okay, so our first of our questions, which of course I'm not going to wait for you to answer with a clicker here, but the Earth's crust is thicker beneath a mountain than it is near the seashore. Why? And so we have our options here. The roots of a mountain are heavier than the mountain at the surface, or mountains sink under the upward buoyant force balance. until, I just read it, mountains sink until the upward buoyant force balances the downward gravitational force, or mantle rock is weak beneath the mountain, or oceanic crust is thin. Well, oceanic crust is thin, that's true, but that doesn't explain why the Earth's crust is thicker between a mountain. It just is a statement. The mantle rock is weak really isn't even applicable because we're talking about something that is flowing kind of fluid. You don't talk about the strength or the weakness of water, right? So that's not even a reasonable comment. So we're left with the top two. The roots of the mountain are heavier than the mountain at the surface. It's not that the roots are heavier, it's that the entire thing is just like a boat. You can think of it like a boat. The higher the mountain, the more you have to displace down below so that you're going to have the weight, the downward gravitational force, balanced by that upward buoyant force. Now, Alfred Wegener, I'm sure we pronounce it something different, but I say Wegener. He came up around 1920s or so, the idea of continental drift. And he proposed that at one time, there was a universal land where all of the different continents were joined together. And so that continent is called supercontinent of Pangaea. How did he come up with this? Well, he didn't look at just one thing. One thing he looked at was the apparent match in the shapes of the continents. If you bring South America and Africa together, they fit together. By the way, I grew up right about there. Now, North America and South America, we have this isthmus thing that kind of gets in the way. Bring the other continents together, they all kind of fit. And he said, okay, that fit makes me think that they used to be together and they broke apart. So then he looked at everything. He looked at the kind of fossils that were in the rock. And he found that the fossils here are very similar to the fossils here. And he looked at the types of rock, and he found that the types of rock here are very similar to the types of rock there. And then he looked at the structures in mountain chains. And he looking at the paleo means old, paleoclimatic evidence is looking at things that indicate what the climate was like in the past. He said that it all matches up. They had to have been together at some time. He had only one problem. He couldn't explain how it happened. And so people were like, sure, yeah, great idea. Tell me how it worked. Ha, 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 ha. So it didn't get any traction because he didn't have a mechanism for how this was going to work. That's why I've labeled these an idea before its time, because it was, we believe, the correct idea. But nobody knew how it would work. Now, studying the ocean floor has led us to a lot of new understanding. We see in the ocean floor huge mountain ranges and deep trenches near the continental boundaries, not in the center, but near the boundaries. So keep that in mind. The deep trenches are at the boundaries between the continents and the ocean. So the deepest part of the ocean is near the shore, not in the center. And so, relatively speaking, it's shallow in the center. It's not really shallow, but relatively. And Harry Hess hypothesized that the seafloor spreading produces a mechanism for the motion of the crust as Wegener had predicted. So here's what we believe is happening. This is the current modern understanding. So we have the mantle down here, and in the mantle, you have some regions where you have magma, hot molten material that flows upward. And that hot molten material then drives convection cycles within the mantle. So you have the motion of mantle going around in a circle. Now this hot stuff comes up to the top and it melts a hole through and punches through. And the motion here of the mantle pushes the place where you punched a hole apart. And so you have the mid-ocean ridge where you have a rift zone where it's being pulled apart. And of course, you have molten magma that gets to the surface here. Water is going to cool it rapidly. And so it freezes rapidly, forming new ocean floor. But of course, the ocean floor then is being pushed toward the continents. And so when it gets to the continent, you have the more dense oceanic and the less dense continental crusts meeting together. And then we have subduction. I just want to here show my hands moving for the subduction, but you have the more dense material then slides underneath the less dense material. So the more dense material is sliding down here. I'm trying to find a color that's going to show contrast. This color would, except for it's just a line. So the more dense slides underneath, and then you have rock grinding on rock. And when you have rock grinding on rock, it's no different than when you have your hand rubbing on a rug. It gets hot. And so it melts rock. And so if you look in this picture, we have molten rock flowing up. And I'm going to go to the other side because something happened I can't erase. We have molten rock made by the grinding that then floats up and makes volcanoes. So where we have oceans meet the continents, we have that subduction, the sliding under, and it causes grinding and melting of rock, and then that molten rock floats up and creates volcanoes, which is where we get the term the Ring of Fire. The Ring of Fire is the ring around the Pacific Ocean where you have subduction, which has caused lots and lots of volcanoes, also lots and lots of earthquakes because of the stresses produced by this grinding. Now, once again, the deepest parts of the ocean are these trenches near the continental boundaries where the subduction is occurring, where it's sliding underneath. And so you have the plains, the ocean plains, that are not nearly as deep as those trenches can get. Now, how do we know anything about this really? It comes from magnetic studies. Sailors, traveling, using their compasses, noticed that as they travel across the ocean, their compasses would just go wild. They wouldn't keep them going the same direction. And so scientists, as you remember from the scientific method, you notice something interesting, then you come up with a hypothesis to explain why. And so the scientists came up with the idea that this, you have mid-oceanic trenches, that maybe magma comes up and it freezes, and we're constantly making new ocean floor. And the Earth's magnetic field is going to then make the little iron particles line up with the Earth's magnetic field and give you a frozen magnet in the ocean floor. And so this has been carefully studied. And here's what scientists have found when they study the ocean floor. You have regions, and if you look here, normal polarities are these colors, and then brown is reverse polarity. Normal is what we have now. So this has the normal on both sides, and then reversed, then back to normal, reversed, normal, reversed. It's a mirror image in terms of the widths of these from one side to the other. And so that agrees very well with the idea that we are laying down new ocean floor and that we're recording information about the Earth's magnetic field. But now then this brings up another interesting thing. That means the Earth's magnetic field has flipped. So what is currently the north magnetic pole, which happens to be the south geographic pole, in the past has been the south magnetic pole. So north and south poles of the Earth has switched over time, which sounds crazy. But we observe that happening in the sun every roughly dozen years. And so we know what happens with the sun, and we have good, strong evidence that it has happened in the past with the Earth as well. So we call this theory the theory of plate tectonics, that says we have the surface of the Earth moving. And so to get into it carefully, we like to think of the surface of the Earth like the shell of an egg. And if you take that egg and you drop it on the floor, it will crack into a bunch of pieces. And so that's what we believe has happened to the crust of the Earth. It's cracked. And so we have 8 large plates and then a number of smaller ones. And these large plates, now on the surface of an egg, they stay fixed. But these plates can actually slide around a little bit and bump into each other. And that motion of the magma coming up is what drives the motion of the plates. The plates are the upper mantle and the crust. And remember, combined, we call that the lithosphere. So these tectonic plates are the lithosphere, and they ride on top of the asthenosphere, which, remember I said I was taught it was like the grease over which they slide. So here's a picture that shows the major plates of the Earth. So you have the Pacific plate, I'll label that 1. You have the North American plate, I'll label that 2. The Caribbean plate, I'll label that 3. South American plate, I'll label that 4. The African plate, I'll label that 5. The Eurasian plate, I'll label that 6. The Australian plate, I'll label that 7. And then we have the smaller plates, which I know it said 8 major plates. Which one's the 8th major plate? The Antarctic plate. So there's our 8 major plates. And then the minor plates, well, this one here, the Nazca plate, that's a real big minor plate for us. You know, they have more earthquakes in Chile than anywhere else in the world. Why? Because this Nazca plate is pushing into it, causing a subduction, putting stress on the rocks. And when the stress gets enough, the rocks slip, and that causes an earthquake. Those Chileans, they live through earthquake after earthquake. Other minor plates, we have the Cocos plate, the plate of Juan de Fuca, the Scotia plate, the Arabian plate, the Indian plate, the Filipino plate. So then we've got, so there's the plates that we have. Now, notice that the motions are not all the same. Here, where the Nazca plate meets the South American plate, the Nazca plate is pushing into it. That's a convergent boundary, converging because they're converging together. But if you look at the other side where the Nazca plate and the Pacific plate are, they're moving away from each other. That's a divergent boundary. And then we have what's going on in California right now. We have the Pacific plate is moving roughly to the northwest, and the North American plate is moving to the southeast. So they're sliding against each other, and we call that a transform. So transform is sliding, and then we have convergent coming together. Convergent coming together, and divergent moving apart. Now let's zoom back in and think about this. You have probably heard that someday, well, 2 things you hear. California is going to fall into the ocean. What does that fundamentally mean? It means that California, which is, like here roughly, that California is going to move from being on the North American plate to onto the Pacific plate. There is some conjecture that on the day that I think it was the day my sister was married, that occurred, that the primary separator between the 2 plates moved from the San Andreas Fault, which Monterey Bay Academy is basically on top of. I grew up on top of that, out to the other side of California. So California at that point may have fallen off into the ocean. Doesn't mean it went underwater. It means it's on the Pacific plate. But a second thing you hear is that someday Los Angeles will be a neighbor with San Francisco. And that's because this motion, if Los Angeles is on the ocean plate, which it is, and San Francisco is on the North American plate, which at least it was, then Los Angeles is moving closer to San Francisco over time. Every time we have an earthquake, there's some slippage, and Los Angeles may get a couple meters closer to San Francisco. Now we're talking a very, very long time until San Francisco and Los Angeles would be neighbors. But that is what people are talking about. They're not just being ridiculous when they say California fall into the ocean or Los Angeles will be a neighbor with San Francisco. But they are probably being a little deceitful or confusing in the way they're talking about it. They're talking about real things and outcomes that you wouldn't really notice. Now, in a million years, you might notice. Continental plates tend to move very slowly. Oceanic plates tend to move faster. Why? We've already talked about the magma is driving the ocean plates, making them move faster. The continental plates don't have those drivers. They don't move so much. The ring of fire is earthquakes, volcanoes, and mountains are caused by the boundaries interacting. In fact, let's go back to this picture. I am currently up in the Rocky Mountains. I live in South Park, 9,400 feet elevation. And so I'm up here on a very tall mountain. How did that mountain occur? What made the mountain? The prevailing scientific theory is that back in the day, the ocean was, what do we call that? A converging boundary. The ocean was coming in and crushing into the North American plate and subducting under. But that converging caused all of this ground to move until it reached a crumple zone. And the Rocky Mountains where I live is where the crumple zone was, where the Earth's crust crumpled because of all of that compressive stress caused by the Pacific plate pushing on the North American plate. And so it built up those mountains. Now, that's not the only. We also have the Sierra Nevada mountains, and then we have the coastal range. So we have a number of mountain ranges there that we believe were caused by the subduction of the Pacific plate under the North American plate. Go forward about 4 slides. I've already talked about these boundaries. If you have a divergent boundary, you have lithosphere formation. You form new crust. And that usually, in fact, it always happens in the middle of the ocean. There's one place on Earth where we have a divergent boundary. It's the Rift Valley in Africa. And at some point, if that continues the process of diverging, we will actually have a rupture and probably have an ocean there. Convergent boundaries, where they come together, you have a lot of grinding, so it creates new magma. It melts rock, and it destroys the lithosphere. And then we have the transform boundaries, what's going on with California's boundary right now. You don't make magma. You don't form or destroy the lithosphere, but you have a lot of earthquakes. So coming back to look at the mid-ocean rifts just a little more, how we're creating new ocean floor. The magma comes up, it freezes, and it starts moving in both directions away because of the motion of the mantle with its convection currents underneath. And like I said, that Rift Valley in Africa is another example where you have a divergent boundary. Okay, here is a convergent boundary. This is the more dense material. This is the less dense material. And the more dense material slides under or subducts under the less dense material. So the less dense material, that's the kind of stuff that continents are made of. The more dense material, that's the kind of stuff that ocean floors are made of. And so where does that ocean trench occur? Right here. The ocean trench occurs where you're having that active subduction. And so you have, now of course it's not all smooth like that. It's roughened up because you have a lot of stuff that falls and whatnot. But that's where you have your ocean trenches near the boundary, well, at the boundary with the continental and the oceanic crusts. And so here you see a more words for more detail of that situation. The lithosphere sliding underneath from the ocean. The grinding is causing volcanoes. It shows these as volcanoes occurring underwater, but of course you may know that there's lots of volcanoes that occur out here as well on the continental crust. Notice there is a flat region here between where the subduction is occurring and where the shore is. That is, you're not going to walk out into the ocean and all of a sudden fall down into a trench. There is that flat plane before you get to the subduction. Notice the lithosphere here that slides down, it's being destroyed. It's eventually going to be melted and just become part of the mantle. And so we're recycling material here in a way. I don't know why I have another picture showing this. This one here, well, the difference in this one is it shows the trench closer and shows the volcanoes occurring on land, and gives us a couple examples. The Andes and the Cascades are additional regions that were created by this process. And this is showing us how mountain ranges like the Himalayas or Himalayas, depending who you are, the Alps, the Appalachians, how they were created by the crumpling of the continent because of subduction. So notice this is continental crust that was being pushed in from the ocean. And so it was crumpling here. This is where it's crumpling. It's kind of a funny story. You know, I'm a creationist. I believe that God created this earth. I believe that he then later created life on this earth. But that doesn't mean I deny science. And the science indicates that these things are going on, and indicates that right now the Himalayas are growing. They're growing because of this converging boundary with subduction. And so what does that mean? That mountains like Mount Everest, they're slowly growing. Now they're also eroding. And so you have two competing things going up and coming down. Back when I was teaching at PUC a long time ago now, there was a man who came and was talking about creation and how evolution couldn't be true. And of course, I mean, I don't believe in evolution either. And so one of his pieces of evidence for creation was the height of, the Himalayan mountains. And he said that, we have erosion that's occurring. And if these mountains are as old as they say they are, and we have this erosion going on, the mountains should have flattened out by now. And my colleague, Dr. Mundy's his name, another physics professor, he asked him, well, I mean, but the mountains are growing. How do you explain that? And he was just dumbfounded. This guy had no idea that the mountains grow. But we actually have evidence. One of the coolest things, I know this sounds dumb, but the summer after my first year of teaching at PUC, I spent the summer acting up in Skagway, Alaska. And so I took in all of the sites up there. And one of the things that I really enjoyed was the ranger tour of Dyea, which was where people went when they were going for the Alaska Gold Rush. They would go there, and then they'd go up and over to the Klondike Goldfields. And the ranger was explaining all of these kinds of things and pointing out that the land there in Dyea goes up about a foot a year because of the motion of the plates. You have where we were up there in Alaska was up around here, and you have material that comes under here and pushes it up. So the ground is rising rather rapidly. And I was just like, wow, that is so cool. A foot a year, that is totally measurable. It's not something that seems theoretical at that point. It's very real. Now, faults, remember I told you faults are cracks. And we have the plate boundaries are the ultimate faults. They're the big cracks. But we have smaller cracks that occur in the earth. And so those faults can likewise, just like you had transform boundaries or converging or diverging, you can have faults that are transform faults, or you can have them so that they are converging or diverging. And so when we have a fault, it's a place where the ground can slip. And so this example is showing where there's a fault here and there's been slippage so that this rift zone in the ocean has been displaced. It's not a straight line anymore because a fault has caused them to slip past each other. here's the San Andreas Fault. And remember, I told you where I grew up. I grew up right here. The road was San Andreas Road because the San Andreas Fault is right there. Up here is San Francisco. It's marked there, San Francisco, and Oakland's over here. That's where the Raiders used to play. And so that's a transform fault, and anything that's on this side is ocean. It's not covered with water, but it's on the ocean plate. And so Los Angeles is on the ocean plate. It's moving north to come up and be next to San Francisco eventually, because San Francisco, it's right there on the boundary. And like I said, there was a theory that with that earthquake that occurred, the boundary might have moved more like that, putting all of California falling into the ocean. Compressional stress. I talked about stress a lot and haven't defined it. Stress is a force applied over an area. So compressional stress when two things are pushed together, tensional when they're pulled apart, shear when they're sliding against each other. And the rocks can elastically deform, just like a spring. They can bend and then spring back when they're released, or they can crumble, or they can flow. So when I was in Japan, I spent a summer doing research in Japan. The guy I was working for was studying brittle deformation of material, studying the electrical signals that are produced when you break rock. And so he put sensors into rock to try to measure the electrical signals of breaking rock to predict when earthquakes were going to happen. I thought it was very interesting research. I don't know how far it's gone. Now, the last couple of things I have evidence for plate tectonics. Normally, sediment is laid down horizontally. So this stuff here that shows the dots, that's sediment. That's like you have an ocean and you have dirt that flows in with the water, settles on the bottom. It forms flat. But if you compress that, if you push both sides in, just like if you took a piece of cardboard, you push both sides in toward each other, eventually it's going to crumple and you form this kind of crumpling. And so you have lower layers here where it curves up on both sides. That's called a syncline. So the low regions are syn, because syn is low. And then the high regions are anticlines. Sorry, I don't have a good mnemonic for that, but the syn is the low region. And so when you see these, like when you're driving down the highway and you have a rock cut on the side, you'll often see them layers like this. That's a sign that you had some crumpling there, some folds. And sometimes it will get so extreme that you can get these so they're vertical or even fall over upside down. A couple more things here. When you have a fault here, the one that's on the lower side is called the footwall. The one that is on the upper side is called the hanging wall. And so this is supposed to help us remember, if you were to separate those two, you could hang your light from the hanging wall and your feet would be on the footwall. Now, if these are converging, moving together, then the hanging wall is going to slide up and the footwall is going to slide down. But if it was reversed, if they were moving apart, if it was diverging, so if it was going like this, then you'd have the hanging wall would slip down. So what happens on those depends on the direction of motion. And so if you have it so they're converging, then you're going to have a reverse fault where the hanging wall goes up and the footwall goes down comparatively. Whereas if they're diverging, then it's going to be normal. So here's the example of they're diverging and it slides normal. Okay, it is time to end the lecture. So let's just look at the Ring of Fire. This is mapping out where you have volcanoes and earthquakes. And so you see very clearly, you have a lot of that action going on here. This is the Nazca plate. This is the Pacific plate. This is the North American plate. And this is what, the Eurasian plate? I don't pay as much attention to that. think that's the Eurasian plate. And the Australian plate is going to be down here. That was my timer saying it's time to end the lecture, not a phone. And so the ring of fire is the boundaries of these plates where you have lots of motion, lots of grinding, lots of crumpling. And you can see other plate boundaries by similar things. All right. Have a great day. I'll see you next time.